Hello, my name is Greg Gilleland. I'm an application scientist with Agilent Technologies, and you have tuned in to my discussion of how the Agilent 5800, 5900 ICPOES systems make your EPA 200.7 analysis faster, easier, and more accurate than ever. Let's dive in. There's three ways basically that the 5800, 5900 will make your 200.7 analysis faster, easier, and more accurate. So we're going to obviously start with speed because that's the first thing on our list. So the speed is enhanced by a few things. First of all, Intelliquant screening, which we will discuss. SVDV, which is synchronous vertical dual view, which I'll discuss, and the AVS 6 and 7, switching valve, advanced valve system 6 and 7, which refers to the either 6-port or 7-port valve. So all of these we'll go into in this little discussion. So Intelliquant screening, this is our semi-quantitative screening for across the periodic table, basically. It costs about 10 seconds a sample when you run it as part of a standard analysis. You can actually do, though, Intelliquant screening, it's about 20 seconds per sample, and you can get 78 elements, a semi-quantitative look at 78 elements in about 20 seconds. So this way you can look at your samples, you know what wavelengths to avoid because of interferences. You also know where to make your standards in terms of concentrations. You don't have surprises in terms of samples that would ordinarily blow you out of the water. So you're actually able to plan a little bit better and see things coming down the road instead of getting that one sample that everybody has had that you spend the rest of the week cleaning your instrument out on. So. In addition to that, you have a number of nice little tools. There's the periodic table heat map, which gives you, like I said, semi-quantitative concentrations across the periodic table, allows you to plan your analysis accordingly. So moving on to SVDV, which is synchronous vertical dual view. So synchronous vertical dual view is basically the ability to look at both radial and axial light at the same time from the same sample, without having to shift views, without having to change the optics somehow, without having to put a mirror into the light path, etc. This allows you to look axially and radially at the same time. And since simultaneous was sort of a compromised term, we decided to go with synchronous. So synchronous vertical dual view is what that SVDV stands for. And what that does is, what makes that possible is a dichroic spectral combiner, which is a patented optic that we have in the light path that acts as a window at the longer wavelengths and acts as a mirror at the shorter wavelengths. So the ultimate outgrowth of that is that the axial wavelengths are reflected, or the short wavelengths are reflected, and they actually comes from the axial view. The longer wavelengths are will go pass through the window, the dichroic spectral combiner, and will go to the detector directly, as you see in the diagram. So you can also run it in a traditional way. You can run it axial only, and in that case, in that spot where you see the dichroic spectral combiner there, you have a mirror, and in that case, there is no radial signal whatsoever. It's all axial. The axial bounces there and hits the mirror and goes to the detector. There's also a way to run it as strictly radial. In that case, you have an open spot in that particular optical spot, and then that's all radial light. or you can run it the way traditional or old-fashioned dual-view systems run, which is to say they'll run all the axial views and then they'll run all the radials, or vice versa, so that they're split up. It just takes longer. This is a time saver, and generally speaking, that time that it takes to switch over to radial view, the time you're looking at the sample for radial view, all that time you can save by doing your samples via SVDV. So, like I said there, it's about 20 seconds faster than conventional systems when you're running the standard 200.7 type analysis. So, the next thing we're going to discuss, like I said, was the AVS 6 and 7, and as I mentioned, AVS stands for Advanced Valve System 6 and 7. The Advanced Valve System, the heart of that is the 6 or 7 sample valve that you see there off to the right of your screen. That is actually the 6-port valve there. So the 7th port is for internal standard introduction. So what this allows is for you to fill a sample loop, and a lot of people are familiar with this technique. Fill a sample loop, and that sample loop is filled with a high-speed pump, which you see on the right, and then it's slowly bled into the nebulizer and then into the spray chamber and plasma, while the front end of the system, the autosampler probe, etc., is all rinsing out. So you're essentially removing all of the uptake time and all of the rinse time from your analysis. So this is a gigantic time saver. It, generally speaking, can shave off 60 to 90 seconds in a typical analysis, because generally you have anywhere from 25 to 30 seconds of uptake time, even at high pump speeds, and a certain, usually 20 seconds of stabilization time. And then you have anywhere from 30 to 60 seconds of rinse time, generally, depending on your system. So you can save a tremendous amount of time just with the AVS. So it is a gigantic time saver. It does have fully integrated hardware and software. There's nothing else that you have to buy. There's no software discussion that has to take place or union. It is part of the instrument, and the software is native to the instrument software. So there's nothing else that you need to learn. It does reduce the cost of analysis by minimizing the time of analysis, obviously, and the use of all the resources that go into analysis. So that's another huge time saver, and another thing that makes your lab faster and more nimble. It is compatible with all autosamplers. No matter what autosampler you're using, you can use the AVS 6 and 7. So you don't need your own special autosampler, or you don't need our special autosampler. So, so that pretty much puts to bed the speed portion of the discussion. The three ways that I said we would make your analysis faster. Now, in terms of ease of use, making your life easier, Intelliquant 2.0. This is another facet of Intelliquant that I wanted to discuss, along with EMF and OCF. And we at Agilent are very, very proud of our 3-letter acronyms. So I thought I'd throw some in for you, but I will tell you what they mean. So Intelliquant 2.0 is just the second generation of Intelliquant. Those of you familiar with our 5100 and 5110 ICPOES systems from a few years back will remember initially Intelliquant. It's a terrific idea. It's a semi-quantitative look at basically the whole periodic table. Intelliquant 2.0 takes that and kind of takes it to the next level by actually giving you a star rating system. When it looks at wavelengths, you can scan your samples. It'll tell you what's in your samples, and it'll tell you what wavelengths it thinks you should use to analyze your samples and which ones it thinks you shouldn't use. So in this case, you've got a star rating system from 1 to 5 stars for all of these emission lines, and then some of them have a question mark, and those question marks indicate problems with those specific emission lines. In this case, you see this boron line is flagged for having very poor confidence, and it's got a big iron interference. So they recommend that you don't use it. And in fact, they tell you which one they do recommend with a green check mark. So it's like having a spectroscopist who's got years of experience and insight right there with you doing your method development. And I realize at 200.7, there's not a lot of method development that goes in, but there's some. I've set up 200.7 methods at many commercial environmental labs, and there's always some level of method development that goes into this, and this would tend to make it a little bit easier. Granted, you don't know what samples are going to come in the door, but this will certainly make things easier when you're developing methods and when you're running a new sample type that comes in the door. So, in addition to that, this simplified list of wavelengths, the ones that actually do have green check marks and were used by Intelliquant, can be copied and pasted into a new worksheet where you can just take this information directly, make a new worksheet, and that is your those are your analyte wavelengths for analysis. So there's Intelliquant 2.0. Let's go to EMF. EMF, love the acronyms, stands for Early Maintenance Feedback. Early maintenance feedback is really a customizable maintenance schedule for your system. You're able to dial all these schedules up based on your specific experience running the instrument, based on your experience with your samples, because nobody knows your samples better than you. It allows you to create new maintenance items. It allows you to customize the existing maintenance items. You can actually have optional pop-up alerts that will actually pop up in the middle of your analysis and tell you that something needs to be addressed. Look at the axial viewing window, change the tubing, clean the nebulizer, clean the torch, etc., etc. All those things are able to be turned into a pop-up that will at least give the analyst cause to either dismiss or reset those items at the instrument. So, in addition, you can actually time the life cycle of each of these items by the number of hours the instrument's actually on, the number of plasma hours you run, the number of samples, or just the sheer number of days since the last maintenance item has gone through. So pretty flexible and really, really handy, especially when you have a lot of users using an instrument. I think it's extremely handy to have something like this in your corner. So OCF, yet another three-letter acronym, which stands for Outlier Conditional Formatting. Outlier conditional formatting is a feature that allows you to actually track 6 QC parameters and to track when you see the failures of these QC parameters. They're customizable. In the case of your result concentration percent RSD, you can have it flagged if your percent RSD for a result is over 5%. But when you get to very low values, all your RSDs are over 5% because they're very low and there's a lot of noise associated with them. So you can actually have that apply only when it's 3 times the MDL or some other multiple times the MDL. So these are kind of scalable to what you want to do with them, but they pop up with nice colored flags on your data so that you can see where the failures happen. And in the case where you have just a gigantic amount of data, which I frequently do, and you want to be able to find those failures, it's handy to actually click. There's a show only failures button, and it will just show you the QC that failed. And then you're able to dial in and figure out what's going on with those specific samples for those specific analytes, which is a little bit easier than trying to find a needle in a haystack looking at, 10 different wavelengths for everything, which is kind of what I do a lot of the time. So it makes it very simple. So those are the three ease of use items I wanted to go over. Intelliquant 2.0, and the ability to have the instrument select wavelengths for you. EMF, so that early maintenance, so that you don't do maintenance more frequently than you need to, but you get the maintenance done in a timely fashion, and it lets you know when the maintenance is due. And OCF, Outlier conditional formatting, where you're actually able to set up your flags so that they intelligently flag your samples, and you're actually able to winnow through all of the data and just find the failures so that you can address them and rerun analysis if need be. So, moving on to the accuracy part of the equation, the accuracy part, as you may have guessed from my previous slides, will probably have three parts: improved resolution, improved detection limits, and improved stability. So I was very impressed, first of all, with our past generations of ICPOES. I've been doing ICP for upwards of 30 years. And these last two generations, the 5100 and the 5110, I thought were just amazing instruments, and I was absolutely tickled with the performance. And so when the engineers came and talked to us about this new generation of systems, and they said, well, the optics are going to be smaller, I thought, oh, what did we give up? What's going to happen? Why would we do this? And so when they presented this to us, they started talking about signal density and things like that. They showed some diagrams taken from the 5110, our previous generation of systems. This happens to be the arsenic at 188. So you see the peak, and you see the signal density on the two-dimensional array, because everything takes place on the two-dimensional chip. So you can see the photon density there. This is without freeform optics. Now, they added a freeform collimating mirror to this system, and this is what it did to the signal density. And it's amazing. The difference between this signal density and this the slope of the spectra is incredible. So much more density, so much better defined. The peak is so much better defined. So the resolution has improved radically. The detection limits have improved radically, just because of this one single optical component. What is this optical component, you ask? Well, let me just quickly show you. This is a diagram, or kind of a mock-up of our optics, the optical tank. The torch would be sitting down here in the lower right as you look at it. So what we see here in the lower left is the detector. So you can see the ray tracing back to the focusing mirror, back through the prism and the grating there at the lower center. And then there's the freeform collimating mirror up in the upper right, bringing it down to the pre-optics and the entrance slit in the lower left. Yes. So the freeform collimating mirror, what is a freeform optic? Freeform optics are not traditionally surfaced optics. They're, in fact, on a nanoscale, they look kind of like a Pringle. And in fact, some people like to call this the Pringle. It looks like a Pringle potato chip. It's not really truly that radical when you look at it, because that is on a grossly exaggerated scale. But What this does is eliminates aberrations in the optical image, because, as you know, in a spectrometer, what you're trying to do is take light, which actually focuses in a there's no flat focus fields in a traditional optical system. So because there's no flat focus, you have to correct for those aberrations that take place on the edge of the field of focus, and that's what a freeform optic does. So not only did we put this in the spectrometer, but we actually came up with a better way to manufacture and replicate these freeform optics. So that is really the big idea behind the 5800, 5900. It allowed us to shrink the optics box, actually by, I believe, I think something around half, about 50% smaller. The optics box is honestly about, I don't know, about 2 feet, maybe a little bit more, and that's it. That's how big the optics box is. It's very small, and so of course the added benefit is that it purges very quickly, and it's easy to maintain the temperature. It gets up to temperature quickly because it is thermostated. So there's a lot of benefits to having the smaller optics. But the performance is where it's at. So what does all this hand wavy optics get us? And hopefully this doesn't get in the way of my slide. It doesn't. So the detection limits that we're seeing for some of the kind of common toxic elements, arsenic at 1.1, cadmium is always great, mercury at 0.3 ppb, lead at 1.1, thallium at 1.1. The percent reduction from the previous detection limits, which were not shabby, is amazing. 70% for arsenic, 70% reduction in the detection limit. So this has made a tremendous difference in the numbers that you're going to get for your low-level metals, especially the difficult metals that you see in environmental analysis, and in the reliability of the data, especially down low, when you're having to run at your CRI or at the very, very low level at reporting limit. This makes those numbers much more reliable. Granted, it's going to push reporting limits down probably, but that's the business we're all in, right? The instrument can do something cool and new, and people start taking advantage of it, and then we all have to live up to that for the next 10 years until it all pushes down again by a factor of 10. So, at any rate, the detection limits and the resolution with this system are incredible, and the performance that you see in a standard 200.7 run is remarkable compared to even compared to the older system, which I thought was very, very good. It's outstanding. So this resolution piece of the puzzle, I would say that's done. The stability is impeccable. So you get all the benefits that you had with the previous system to begin with, and you have the greatly enhanced performance that freeform optic is giving you. So the speed, the ease of use, the accuracy all come together, but I'm sure you knew that there had to be some more, so there is going to be an etc. piece to the puzzle. And the etc. Comes in the form of a few other things that didn't get mentioned along the way, but I will throw those out just as a kind of an aside so that you're aware. So we talked about outlier conditional formatting. We talked about early maintenance feedback. Let's talk about NebAlert and some other things as well. But what all these kind of come together to form is something we call smart tools. And smart tools will help you gain insight into your instrument operation and reduce remeasurement. That's the whole idea. These things, it's information that we can provide to you on the instrument and how it's operating so that you can take corrective action and keep your instrument up and running properly so that you don't have to go back and rerun stuff, because nobody's making any money if they're having to rerun stuff. And nobody's having any fun if they're having to rerun stuff. So at the bench, it's no fun because I've been there. And in the front office and the corner office, it's no fun because you're not making money. So these things are important to everybody at any position in the laboratory. So let's talk about things like the NebAlert. NebAlert is it's a monitor. It monitors the back pressure of your nebulizer, so it can actually tell if your back pressure suddenly spikes up. It's pretty sure that there's a blockage in your nebulizer. It will alert you of that, and you can set it up so that it actually gives you a pop-up on your screen that says, hey, we think your nebulizer is blocked. It will also, in the same vein, as it's monitoring your back pressure, if that back pressure crashes and there's just no back pressure anymore, then it assumes that the nebulizers come unconnected or something to that effect, and it will give you a pop-up message as well. So rather than running all day or all night with a nebulizer that's crashed on you and wasting all that sample, all those resources, which is soul killing, I know, because I've been there. This will allow you to stop it. It'll stop your run, and you can go back and take care of things. Clean up your nebulizer, replace the nebulizer, and start over, what have you. Stuff you wouldn't know until maybe you came in the morning, or somebody else happened to look at or go over and look at the data. This actually gives you a pop-up message that indicates that there's a problem. So I think that's really cool. As someone who's done this, intelligent rinse is something that we added in this version of software. Now this isn't something where it rinses different times. It will only rinse a maximum amount of, in this case, it'll ask you what your max rinse time is, and we set it at 60 seconds. But that's the most it will ever rinse. But what it will do is monitor the lines that you specify at the levels that you specify, and if it returns to the same stable baseline that it determined before the analysis, then it will stop rinsing. For instance, if you are running brine samples and it returns back to the previously determined stable baseline for sodium, it will keep going. And if it hasn't, it will rinse the maximum amount, and then it will tell you if it still hasn't reached the baseline for certain wavelengths. This is really handy because you don't want to use more rinse than you need, but if you're running some especially unknown samples, you have no idea what they are, or if you know they're nasty, maybe you do want to put in some really long rinses. But say when you're coming off of the blank, or you're coming off of some your prep blank, etc., you don't need to run those awfully long rinses. So you can save some time and save some rinse solution by not running fast pump for 90 seconds or what have you, and just back that down to only when you need it. I like this feature. It's very useful, and it keeps things more efficient in the lab. So there's also the internal standard monitor that we introduced. It's not this version, but it was a couple of versions ago. Those of you who are familiar with our ICPMS products will probably be familiar with the way this looks. Just tracks the internal standards. You can see if you have an internal standard crash out. You can see what the trends are. In this case, it's pretty mellow. I think that's all plus or minus 10% if I'm reading the scale correctly with my poor eyesight. But at any rate, this is a handy tool, and it actually identifies what the standards are there, so you can see which ones are good, which ones are not, if so, and act accordingly. In addition to that, there's a couple of other features. We won't go back on that. We'll just stay where we are. So in addition to those smart tools, there are a set of smart tools that give you insights into your samples. We've already talked about Intelliquant screening. We've talked about spectral interference identification and ways, the way that Intelliquant helps you understand your sample's composition. A couple other things to mention. Intelliquant also helps you identify what kind of sample prep problems may have taken place. The nice thing I've seen in Intelliquant is you get a chlorine number. Say, for instance, there's HCl, hydrochloric, used in your sample prep, or there's supposed to be. If you don't see chlorine, then you don't have HCl in your samples, and that maybe there's a prep problem that you can identify immediately. Conversely, maybe someone did use HCl and they weren't supposed to. You can identify that as well, and you can nip that in the bud and get your samples prepped properly. So you don't go through the whole prep process, or the whole prep process and the analysis process, and then realize that they were prepped incorrectly. So there is that. There is also the argon emission monitor, which I find pretty useful. It really just tracks the emission of a certain suite of argon lines, and allows you to look at them for each sample that you ran. So this sort of allows you to track the plasma efficiency, how hot the plasma was, whether or not there was any issue with sample interruption, sample flow interruption, or anything like that along the way. Or if there was some sort of massive suppression because of sample matrix. You can certainly see the arsenic emission hit the floor. Occasionally it will do that as well. So there are ways to, this is a very useful technique to be able to use things like that. So moving on from ways we can help you make your analysis faster, easier, and more accurate, there's sort of what's coming up on the horizon for environmental topics. The EPA is working actively on UCMR 5, and that is a list of emerging contaminants that are likely to be added to permits in the future. They're at least going to be studied. And so that process is going on right now. I think it was a little bit delayed by the COVID-19 issue in 2020. It was a great year, wasn't it? So at this point, it's actually in pre-publication. It's under review as of the 20th of last month. Once it's published, the EPA will host a couple of identical webinars, and they'll discuss the lab approval process for this for the pilot study, laboratory methods, and monitoring requirements. So all this will be discussed. So this whole process is kind of well, it's something that the EPA goes through about every 5 years, where they add contaminants. In this case, a lot of the contaminants that are being added are PFAs. They've been a lot in the news, these plastics that just don't go away in our environment. But the one that they've added for of interest, 200.7, and then those two run 200.7, is lithium. So if you have not or are not looking at lithium, it might be a good idea to start including that into your program. It's something that is going to be coming up before long, and if your laboratory would like to get on the cutting edge and maybe help the EPA collect some data, then that is certainly something you can do. There's a whole landing page for UCMR 5 at epa.gov. You can get involved and you can apply to be part of the proficiency monitoring process. So I think that's all that I had for now. Thank you very much for your attention. I appreciate it, and I look forward to talking to you again next time. And thank you for your participation. And I will be around for questions during the live virtual environmental summit. Thank you. Bye-bye.